In this video, we're going to talk about the matrix for a transformation T relative to bases B and C. So I want to begin by just doing a brief overview of sort of the progression that we've made when talking about coordinate vectors. So back in chapters 1 and 2, we were always looking at what I'll call the standard coordinates. Standard coordinates in Rn. Okay. So we were just looking at a vector x sort of represented in the normal way. In section 4.4, we looked at vectors in terms of their coordinates, and we were working in arbitrary vector spaces sometimes, so not necessarily just Rn. So coordinates in V, where V is some vector space. And some of the terminology, some of the notation that we saw, was stuff like we wrote x as a coordinate vector in terms of some basis, B. And we formed this change of coordinates matrix. This changed the coordinates from whatever the basis B was to the standard basis. So in section 4.7, we generalized that a little bit more, and we talked about change of basis. Well, how do you go from one arbitrary basis to another arbitrary basis? So not necessarily the standard basis, like we were doing in 4.4. So we were trying to go from one coordinate representation of x, let's say in terms of the basis b, to another one. So thinking about x in terms as its coordinate vector in terms of some basis c. So these were related. And we saw that in section 4.7. Now, in this section, 5.4, what we're going to be doing is we're going to talk about matrices of abstract linear transformations. So not only will we be doing stuff with coordinate vectors, like we did in 4.4 and 4.7, but we're going to be throwing linear transformations into that. So the main reason we do stuff with coordinate vectors, so that's all of the stuff in section 4.4 and 4.7 and even now in 5.4, is using coordinate vectors, especially on abstract vector spaces, lets us convert questions. I'm just going to write Q's to represent questions about objects in V, whatever our vector space is, even if it's an abstract vector space, to column vector questions. Column vector questions. Because that's what all the coordinate vectors are. The coordinate vectors are now just column vectors, even if the initial elements weren't, if they were something like polynomials or matrices. Okay, so let me now start to get into 5.4 stuff. So I want to begin with some context. So let's let T be a linear transformation from a vector space V to another vector space W. Let's let B be a basis for V. So I'm going to say that B has the vectors B1 up until Bn in it. And then C is a basis for W, and it has elements C1 up until Cm. So it doesn't necessarily have to be the case that M and N are the same. The number of basis vectors in these two sets might be different. Okay, so I want to give a visual picture for what we're about to do. Okay, so imagine that this oval or this circle represents V. And then imagine that this circle or this oval represents W. Okay, so within V, we have some vector x. And what I'll do is, now let's apply the transformation T to x. And when we do that, when we apply the transformation T, it'll give us T of x. And T of x is going to be an element in W. That's the output. Okay, so V and W in general may be abstract vector spaces. They might be abstract vector spaces. Okay, so sometimes what we like to do when we're working with abstract vector spaces is think about the elements in terms of their coordinate vectors. Okay, so let's do that with both the input and the output. So if I think about x in terms of its coordinate vector, so its coordinate vector, let's call this x b, and it's xb because the basis for the vector space v we said was b. Okay, so we're thinking about x in terms of its coordinate vector. We could do the same thing for this output. We could do the same thing for t of x. We could think of that in terms of its coordinate vector. So this is going to be t of x's coordinate vector, but the basis for w was c. Okay, so this is going to live inside some circle. Okay, so each of these coordinate vectors is a column vector. So xb, for example, this is a column vector. Column vector in what? It's a column vector in R. Well, the basis for b has n elements, b1 up until bn. So when we form this column vector, we would be taking the weights of those n basis vectors. So there's n weights. So this is a column vector in Rn. So with that same reasoning, this coordinate vector is also a column vector. But this one is going to be in Rm because the basis for C has m elements in it. So the nice thing about these two sets here, so both of these green circles that I've sort of circled, are that these are column vectors. And those are usually easier to work with. And we've seen this before in problems that we saw back in chapter 4 when we were working with polynomials. Often what we did is we converted them into their coordinate vectors, into column vectors. So what we want to do now is ultimately we'd like a way to start with this coordinate vector, x in terms of the basis b, and go directly to the coordinate vector of t of x in terms of the basis c. So since both of these are column vectors, xb is a column vector and then txc is a column vector, the thing that's going to get us from one of them to the other is a matrix. So I'm going to call that matrix M. So our goal in this section is basically how do we figure out what M is? So I've written that down. Our goal is to find the matrix M such that when I multiply M by this B coordinate vector of X, what I'll get out is the C coordinate vector of T of X. Okay, so next, I want to give a formula for what this matrix is. Okay, so I want to state a definition in which I'll write down a formula for what that matrix is. That lets me go from one set of coordinate vectors to the other one after we've applied T. So if T is a transformation from V to W and it's linear, and just like before, we have a basis B for V and a basis C for W, we're going to call that matrix M the matrix for T, for the transformation, relative to B and C, relative to these two bases. And the formula is, it's going to look really similar to the formula that we saw for change of basis. The only difference is now we're also applying the transformation T to all of the basis vectors of B. So the first column is T of B1, and then take the C coordinate vector of that. Up until the last column is T of Bn, and then take the C coordinate vector of that. And the key is that this matrix M should satisfy this equation right here. Right, and we had written this down before. So multiplying the B coordinate vector of X by this matrix M should give us the C coordinate vector of doing T of X. Okay, so I want to break down, what both sides of this are saying. So when we talk about this B coordinate vector of X, what this does is we're converting a vector, the vector X, to coordinates. And we're doing that first. So we'd be doing that first. And then we're going to multiply by the matrix M. So multiplying by the matrix M, so we'll do that second. M what that does is that just transforms from Rn to Rm. So it's a normal like column vector transformation. So on the other side, t of x's c coordinate vector, this is sort of doing two things, because there's an inside and there's an outside. This does two things. So t of x, that's what happens first. We first transform x, whatever x is. And then after that, we apply the c coordinate vector to that output. So then we write the output in coordinates. So this matrix M gives us another way of doing these two things, like transforming x and then writing the output in C in terms of coordinates. The matrix M is going to give us another way to do that by first converting x to the in terms of its b coordinates. Okay, so there's a special case of this definition where the codomain W is the same thing as the domain V. So I want to state that next. So it'll look really similar to what the formula that we just had. So here's the special case. So if W is the same thing as V, then we call this matrix the B matrix for T. So now there aren't two different bases. Now, because I just have one vector space V, I'm just going to be working with one basis for that vector space, which I'll call B. So then we just call this the B matrix for T. In the textbook, it also calls this, I think, the matrix for T relative to the basis B. So you might hear that terminology. But the formula is the same thing as before, except for instead of having a basis C, notice that all of those C's have been changed to B's because we just have one basis. And then this matrix M, the notation is we write T and then brackets around it and then write B as a subscript. But this just still refers to that matrix M. It's just a new notation for it. And just like before, this needs to satisfy this equation right here. So notice that we've replaced the M with this new notation for this B matrix for T. So if I break down what this is saying as well, so let's think about what the right hand side is doing. So first let's do what this coordinate vector does. So the coordinate vector means, well, let's write the vector x in terms of its coordinates. Write the vector x in terms of the coordinates. And then applying this matrix to that transforms, so matrix is a type of linear transformation. It transforms, but in Rn. So I don't need to say like Rn to Rm because the domain and the codomain are the same here. So we're going from Rn to Rn. So on the other side, T of x and then doing the B coordinate vector. So there's sort of two stages to that. First, we're transforming whatever that vector x is, and the vector x is in the vector space V. And then we're writing that output in coordinates, in terms of the B coordinates. So on both sides, at some point, we're transforming a vector. And we're also writing something in terms of coordinates. We're just doing it in a different order. Okay, so these two formulas that we stated, where do they come from? So where does the formula come from? Well, so the derivation for this is actually really similar to how we derived our change of basis matrix formula back in 4.7. And you can find the derivation in the textbook. But because it's really similar to the derivation that I did in the earlier video in 4.7, I'm going to skip that so I can have more time to devote to examples. Okay, so let's do an example now. We've talked a lot about theory. Let's do an example. So let's say that T is a transformation that goes from R2 to R2. And T of the vector 1, 1 equals 6, 9. And T of the vector 2, 3, when I plug in the vector 2, 3 into T, I get out the vector 1, 1. So the vectors 1, 1 and 2, 3, they're basis vectors. And I'm calling the basis B. So we want to find, in this case, the B matrix of T. So this is the special case where the domain and the codomain are the same. And that's where we're finding the B matrix. So recall the notation for this. The B matrix of T, the notation is we would write T and then put this B in the subscript. Okay, so let's talk about how we'd solve this. So we want to know what the B matrix is for T. So let's write down the formula. So we take T and we input all the basis vectors of B into it. So I'll do T of B1, and then I find its coordinate vector in terms of the basis B. And then I go to the next basis vector, so I'll do T of B2, and then I write that in terms of write that as a coordinate vector. And this is actually where I'd stop because my basis only has 2 vectors in it, so I stop at T of B2. But if my basis had had more elements, like if it had 4 elements in this basis, then I would have gone into T of B4. Okay, so now let's plug in these basis vectors. So B1 is, I'll say it's that first vector here, 1, 1. So I want to plug that into T, and then take its B coordinate vector. And now let's plug in B2, so that'll give me T, and then plugging in the vector 2, 3. And then take its coordinate vector. And these are the columns of the matrix. So let me put the matrix brackets in green, so it stands out a little bit more. Okay, so now let's continue to simplify. So what's T of 1, 1? Well, that was given to us. That's the vector 6, 9. So we have the vector 6, 9. And then we want to find the B coordinate vector of that. Okay, and then T of 2, 3, that was also given to us. That was the vector 1, 1. And we want to find the B coordinate vector of 1, 1. So we want to write 1, 1 in terms of its B coordinates. So these are the columns of our matrix right here. So how do we get these B coordinate vectors? So let me talk about this on the side. So for example, if we want to write the coordinate vector for 6, 9, what we need to do is we need to write 6, 9 as a linear combination of these basis vectors. So we need to write it as, something times B1, which is the vector 1, 1, plus something times B2, which is the vector 2, 3. And let me try to separate this so I don't think that this is equal to what I had here on the right hand side. So now I got to think about what those weights of this linear combination would be. So one thing to notice is that 6, 9 is a multiple of 2, 3. In fact, it's 3 times 2, 3. So that means I would just take 0 times 1, 1. So at this point, these numbers, the 0 and the 3, they're the entries in what the coordinate vector is. Okay, so I know that the coordinate vector for the element 6, 9 is now 0 first, because that was the first weight, and then 3 next. So that's going to be the first column of my matrix. Well, let's do the same thing for 1, 1. So for 1, 1, I also need to write 1, 1 as a linear combination of these basis elements of 1, 1 plus something times the other basis vector, which was 2, 3. And this one actually I think is easier to see. So this one's easier to see because this is just 1 times the vector 1, 1 plus 0 times the vector 2, 3. So the 1 and the 0 are the entries of this coordinate vector. So I'd have a 1 first and then a 0 second, and then I close off my matrix. And that's T of B right there. So that is what we were after. Okay, so that is our B matrix right there. In fact, let me say that this is T of B. That is what we were after. So in this example, we were working with just vectors in R2 for the inputs and for the outputs. So where this matrix version of the transformation can be particularly useful is when working with abstract vector spaces, like with polynomials. So let's do an example of that next. Okay, so this next example, let's let T be a transformation from P2 to P1. And what the transformation does is it takes in a polynomial, p of t, and it outputs the derivative, p prime. Well, I've written that in another way here. When I plug p of t into t, my transformation, what that equals is the derivative, p prime of t. So I'm going to let b be the standard basis for p2. So that has 1, t, and t squared in it. And then c is going to be the standard basis for p1 for this codomain. And that contains 1 and t. So this time, let's find the matrix of t relative to the bases b and c. Okay, so this time we are talking about our first formula. In fact, let me put this in a different color. Let's put this in green. This time I want a formula for m. So we're not after the b matrix, because there are two different bases here. There's a b and a c. Okay, so let's solve this. So this time we're going to be using our other formula. It was actually the first one we introduced. So the formula for m is we plug in b1 into t first, and we take its coordinate vector in terms of the basis c. And then I keep going like this. So there's another basis element of b. So I'll plug in that next basis element into t, and then take its c coordinate vector. And in total, there's 3 basis elements in b. So I would stop at t of b3, and writing down its c coordinate vector. Okay, so let's simplify. So b1, I'm going to say that's this first polynomial here. I'm going to say b1 is just 1. And then I got to take its c coordinate vector. b2, let's let b2 be t, so I'll take t of t, and then take its c coordinate vector. And b3, let's let that be the t squared, so I'd be plugging in t squared into my transformation, and then writing down its c coordinate vector. Okay, so what is t of 1? T of 1 means take the derivative of 1, and we know that that's 0. So t of 1 is 0, and then I gotta still write that as a coordinate vector. Okay, so from here it gets a bit quicker for these other two. The derivative of t is 1. So that's what capital T of lowercase t is. It's 1. And then I gotta find its coordinate vector still. And the derivative of t squared is 2t. So I would need to write that as a coordinate vector. Okay, and let's close off this matrix right here. Okay, so the next thing that I need is, I need to be able to write these polynomials, the 0, the 1, and the 2t, as coordinate vectors relative to this basis c. Okay, but we've seen how to convert polynomials to coordinate vectors in terms of the standard basis before. Let's just do a quick review. So for something like 2t, let's put this in a different color. For something like 2t, let's go to gray. 2t, how would I write that in terms as a linear combination of 1 and t? Well, it's 0 times 1 plus, let's put this in parentheses, plus 2 times t. So notice that the weights are the 0 and the 2, and those are going to be the entries of my coordinate vector. So the coordinate vector that 2t becomes is going to be, let's write it over here actually. I'll have 0 first and then 2 second. Okay, so if we did that same thing for 0, well 0 is definitely going to be 0, 0. And then the coordinate vector for 1 would be 1 for the constant term coefficient, and then 0 for the coefficient of t. Okay, so it might not be, immediately obvious why this is useful, but this is actually very cool. This is actually very cool because this matrix encapsulates taking a derivative. The concept of differentiation encapsulates differentiation. So we can actually completely describe how to take a derivative of something in P2 using this matrix. So let's look at a quick example to illustrate how is that happening. So as an example, let's say that we take the polynomial p of t, which is 3 minus 7t squared. So we can take the derivative of this. p prime of t, this derivative would be negative 14t. Okay, so how does this matrix now encapsulate that information? So, well, if we take p of t and then find its b coordinate vector, so how we write this in terms of the standard basis for p2, well, 3 is the constant term. There's no term with just t, so that coefficient is 0. And then the coefficient of t squared is negative 7. So that's the coordinate vector of p of t. And then if we write the coordinate vector of p prime, the basis here that I want to use is c. Okay, and c, let's remember, was a standard basis for p1. It has 1 and it has t in it. Okay, so I would have 2 entries for this vector. There's no constant term, so I'd have 0 first. And then the coefficient of t is negative 14. So as a check now, if we multiply m times p of t's coordinate vector in terms of b, and let's do that. So the matrix M was this over here. It's 0, 0, 1, 0, 0, 2. Okay, so let's multiply that by this coordinate vector, 3, 0, negative 7. And if we multiply this out, we'll end up getting 0, negative 14. Because this ends up being 3 times the first column, plus 0 times the second column, minus 7 times the third column. But notice that this is the same thing as p prime's coordinate vector in terms of c. So this matrix represented taking the derivative. But once I thought about all my polynomials in terms of its coordinate vector. So that's really nice. It's really nice that a matrix can encapsulate what an abstract linear transformation is doing in terms of just specific numbers like this and column vectors.